Our modern world, it runs on a silent, invisible network of power. But what happens when a key piece of that network, something absolutely vital, is about to fail? Well, today, we're looking at a fascinating new way to prevent catastrophic blackouts by teaching an AI to listen for the whispers of a machine in distress. Okay, let's dive right in. You know, deep inside our power grid, there are these massive, incredibly expensive, and absolutely critical workhorses, power transformers. We don't really think about them, but they're the unsung heroes responsible for getting electricity from the power plant to our homes. The thing is, they're also surprisingly vulnerable. And what's really wild here is the sheer scale of the investment. These machines are built to last for decades, sometimes up to 60 years. The research paper we're looking at calls them one of the most vital and expensive pieces of equipment in the whole system. So yeah, you don't just, swap one of these out like a light bulb. And the stakes? Well, they couldn't be higher. This quote from the researchers really puts it bluntly. When one of these transformers fails, it's not just some minor inconvenience. We're talking catastrophic consequences, widespread power outages, huge financial losses, and it can even be a direct threat to people's safety. So that brings us to the million-dollar question. How do you know if one of these giants is on the brink of failure? It's a really high-stakes diagnostic challenge that engineers have been trying to nail for years. So, historically, there have been two main ways to go about it. On one hand, you have the old-school offline methods. Think of it like a major annual physical, where you have to completely shut the power down. Sure, it's accurate, but it's incredibly disruptive. On the other hand, you have the more modern online methods, which monitor the transformer while it's still running. But as you can guess, they've got their own set of problems. And here's where those problems really start to stack up. For starters, some of these techniques only work on specific types of transformers. Others are just way too expensive, and a lot of the time, they're just not accurate enough to be reliable. But the real kicker is that last point. They often need a highly trained human expert to make sense of the data, and that just doesn't scale. This is where the research we're talking about today gets really, really creative. The core idea is, what if instead of the old methods, we just listened? Listen to the transformer's unique hum, its vibrations, and then turn that sound into a picture that an AI could analyze. It's a brilliant leap from vibration to vision. And the solution they came up with is just beautifully elegant. It's a simple three-step process. First, you use sensors to capture the raw vibration signals. Step 2, use a really clever technique to convert that sound signal into a 2D image. And finally, step 3, you let a powerful AI classify that image and tell you exactly what's wrong. So how on earth do you turn a sound into a picture? Well, the secret sauce is a process called the Continuous Wavelet Transform, or CWT. Basically, it's this incredibly powerful math tool that takes a simple vibration signal and just unfolds it into this rich, detailed image that shows all the different frequencies over time. And what you get is pretty amazing, a unique visual fingerprint. Every single state of the transformer, whether it's running perfectly or has a specific fault, creates its own distinct, colorful image. A healthy hum just looks different from the hum of a loose part, creating a really clear visual pattern for an AI to learn. Okay, so you've got these visual fingerprints. Now you need someone or something that can actually read them. The next step is to train an AI to become an expert at it, to create a master diagnostician that can spot trouble in an instant. And for that job, the researchers used what's called a convolutional neural network, or CNN. This is a special type of AI that's basically designed for recognizing images. It's actually inspired by how our own visual system works, which makes it the perfect tool here. Think of it like an AI radiologist, trained to spot tiny anomalies in an image that a person might totally miss. But of course, to train an AI, you need data. A lot of it. And the researchers couldn't just wait around for real multi-million-dollar transformers to break. So they went into the lab and carefully simulated all these different conditions: normal, healthy operation, and then 4 really common but critical types of faults, like a loose clamp or a short circuit. This gave them a whole library of these visual fingerprints for the AI to study. So after all that setup, all that training, the big question is, did it actually work? Well, the researchers put the AI to the test, and the results were, well, they were pretty astounding. Just look at that number. The average diagnostic accuracy of this system was 99.95%. That's practically perfect. It means the AI could correctly identify the transformer's condition, whether it was healthy or had a specific fault, almost every single time. But that number by itself doesn't even tell the whole story. You have to see it in context. When you compare it to other advanced AI methods like an artificial neural network or even another kind of CNN, this new method just blows them out of the water. This isn't just a small improvement, it is a massive leap forward in diagnostic power. And it's not just about being right, it's about being fast. According to the study, once the AI is trained, it can take a brand new vibration signal, process it, and deliver a full diagnosis in under 7 seconds. For real-time monitoring, that is an absolute game changer. So what does a fast, ultra-accurate tool like this mean for the big picture, for all of us? Well, it points toward a future with a smarter, more resilient, and ultimately a much safer power grid. What this tech really allows for is a huge shift in philosophy. We can move away from reactive, scheduled maintenance, fixing things on a calendar whether they need it or not, to something proactive called condition-based maintenance. We fix things right when they start showing signs of trouble because we can finally see those signs. And the real-world benefits here are just huge. It means we can catch problems at the earliest possible moment. It means we can minimize damage to incredibly expensive equipment. And most importantly, it means we can prevent those catastrophic failures that lead to blackouts. It makes the entire grid that we all depend on safer and way more reliable. This whole breakthrough really leaves us with a fascinating final thought. This technique, turning invisible vibrations into visual data for an AI, could be used almost anywhere. So it makes you wonder, what other invisible machine whispers could AI learn to hear? And what other huge problems could we solve just by learning how to listen?